In this video, we're moving on to talk about the second half of consumer products. So we've already looked at the alcohols homologous series, and now we're moving on to talk about the carboxylic acids. And that is the second of the two new homologous series that we're going to learn about. So as I've just said, carboxylic acids are another example of a homologous series. So remember, we're thinking about compounds that all follow some general formula. And they all, remember from the last video, contain a functional group that indicates what homologous series that these compounds are from. So this time, the group that we are looking for is called the carboxyl functional group, which is why the group is called the carboxylic acids, because they have a carboxyl functional group. And it looks like this. So we have a little bit more complicated this time, but it's easy to identify because it is so complicated. We have a carbon atom, double bonded to an oxygen. That's called a carbonyl group if it was on its own, but we don't need to know that until higher. And then that carbon, the same carbon that's double bonded to this oxygen, is also bonded to an O and an H. Now if we cover up that complicated carbon looking bit, this should be familiar to us. This is actually just like a hydroxyl group from the alcohols joined onto the side here. But when we have the whole thing, when we also have this carbon and double bond oxygen, it means the whole thing is a carboxyl group. Now, I say it's a little bit more complicated, but that is actually good because it's easy to spot in the molecule. And it's also always contained at the end of the acid molecule. So unlike the alcohols where we could find the hydroxyl group in the middle or at the end of the chain or anywhere really, joined onto any of the carbons, this functional group to exist has to be on the end, so it's easy to spot. Now, when we name our molecules, it's a little bit easier again because of that feature. So all the carboxylic acids have a name which ends in anoic acid. All right. So for example, if I look at these two compounds at the bottom of my page here, I have the two simplest carboxylic acids. The first one contains one carbon, the second contains two. And all we're going to do is think back to the prefixes that we've already used to describe how many carbons are in a molecule. So we should already know that if we have one carbon, the prefix we have to use is meth. And if we have two carbons, the prefix we have to use is eth or eth, and then prop and but and pent and so on. So that's all we have to do. That's the missing piece here. So we know it's some kind of carboxylic acid because we have a carboxyl group here and here. So all we have to do is fill in what that prefix would be. So in the first case, it's methanoic acid, methanoic acid. And then for the second one, two carbons, eth, so it becomes ethanoic acid. And that really is it. There's no extra bits that we have to know for the naming, other than if we have perhaps branches further on down the line. But we're experts now in naming and numbering branches. So the only thing that's left to identify here is the general formula for this homologous series. So if we look, we always do the same with our carbons. We always say, okay, well, if I have n carbons, okay, a whole number of carbons, 1 and 2 and 3 and 4, then what do I have to do to the hydrogens, and then what is my functional group? Because remember, we always want to identify the functional groups separately. So in this case, very similar to the alcohols, we're going to have the hydrogens being times by 2, depending on how many carbons there are, and then we add 1 on. Okay, that's that 1 at the end there and there. And then we simply write in what the functional group is. In this case, it's COOH. COOH. So that is my general formula for the carboxylic acids. Now, one of the things we have to look out for when we are drawing and naming our carboxylic acids is that we now have quite a few different ways that we can draw a formula and that we can name compounds. So what I'm going to do, I'm going to take the next member of this homologous series, which is propanoic acid, and we'll see how many ways that we know now how to draw and write about this compound. So propanoic acid, what does that tell us? Well, it tells us that it's a carboxylic acid because it ends in that anoic acid. So we know we're looking for a COOH functional group. It it starts with prop. So we know that there's going to be 3 carbons in total. And it says acid at the end, so that just confirms that we know it's a carboxylic acid. So one of the first ways that we could describe this molecule with a formula is to draw its full structure. Now remember, full structural formula shows us all the atoms, all the bonds, so that's what we're going to do. So the way I would start is with the correct number of carbons. That's always a good place to start with my carbon backbone. So I'm going to go 1, 2, 3, because I know there's 3 carbons because it's propanoic. And then I'm going to fill in my single bonds. And now I'm going to be very careful because I don't want to get into the habit of just putting single bonds around everything. That's not a good idea because sometimes there's double bonds involved, like in this case. And we do have to be careful because one of our carbons is going to be involved in the functional group, remember. So we're going to start there. And I always like to draw it at the right-hand side. So we know we need our double bond to an oxygen atom, and then we need our oxygen and hydrogen. Okay, so what does that tell us? That tells us around this carbon here, I have 1, 2, 3, 4 bonds. And remember, 4 was the magic number of bonds that we need around every carbon. So that tells me to be careful and not add any extra bonds coming off the bottom here because we don't need any because of this double bond. And then all I have to do is go through each of the other carbons and make sure they all have 4 bonds as well. So around this one, 1, 2, 3, 4. Around this one, 1, 2, 3, 4. And then all I have to do is add in the rest of my hydrogen atoms that belong in the main chain. Have a double check. Is it a carboxylic acid? Yes, because it contains my functional group. Is it propanoic acid? Yes, because it has 1, 2, 3 carbons. Okay, so that's one way that we could draw the formula for this compound. And I would argue that's the best way because it gives us the most information about the structure. However, we could also have the shortened structural formula, which if you remember from the last video, is very similar to the full structural formula, except it doesn't show us all the bonds. So I would start from the left-hand side and work my way through. So here's how I would do this. Take each carbon in turn from the full structure and describe what is going on directly attached to that carbon. Okay, so the first one, on the left, I have a carbon, and attached to that carbon, I have 1, 2, 3 hydrogens. So that's what I'm going to write, H3. I can now move on to the next carbon. What do I have attached to that that isn't a carbon? Well, I've got 1, 2 hydrogens, so let's write that in too, H2. Okay, nearly there. On my last carbon, and this is where we have to remember this, when we are writing this functional group, we describe it as COOH. And in chemistry, it's just implied that one of these oxygens is double bonded up to the top of the carbon, and the other oxygen is single bonded onto the end. That's just something that we have to remember. It's like a shorthand in chemistry. So that would be my shortened structural formula for this compound. These mean exactly the same thing. However, there is one last way that we could write the structure, and that is using an even simpler molecular formula. And the molecular formula just tells me the totals of all the different types of elements that there are, in terms of how many atoms there are, and make sure to still include the functional group separately. So we can have a total number of carbons in the main chain, and this is where it might get slightly confusing. We're going to write C2 instead of 3. We're going to describe how many hydrogens are attached to those carbons, which is 1, 2, 3, 4, 5. 5 hydrogens. And then separately, we're going to include our functional group. Now, the inclusion of that carbon atom in the functional group explains why I've only used 2 carbons in my carbon part of the molecular formula, because we have to always include the functional group separately. So always be careful if you're given a molecular formula for a carboxylic acid. Don't be fooled into thinking that this is ethanoic acid because you immediately see the 2. You have to count every carbon. So there's not 2 carbons in this molecule, there's actually 3. And I know that seems obvious because we've just taken our time and went through this in detail, but if you're only given this, and you have to name this based on the molecular formula, just make sure to always count every single carbon in the molecule. And just to prove to ourselves that this is definitely correct, what we can do is match this up with the general formula. Okay, so we're going to write CN H2N plus 1 COOH, and we're going to see if it fits. So we have to substitute in a 2 for N. So let's see, we've got C2, and then to figure out the correct number of H's, if we ignore this one just now, we're going to work with our formula. We have to substitute in 2 for N, so that's going to be 2 times 2, and then we're going to add a 1 to that answer, and then we've got our functional group at the end. Okay, which gives us C2, H, 2 times the 2 is a 4, add on the 1 gives me 5, COOH. And if we look here and here, it's the exact same. So we know that this way of doing the molecular formula works because it does in fact fit our general formula for the carboxylic acids. Now, one last thing we should speak about here is, well, why are we talking about the carboxylic acids and the alcohols separately? Well, because we've identified them as consumer products. And we could mean a couple of things by that. We could mean that they're important to the consumer in society. They're used for a wide variety of consumer needs, or they are consumed within many useful reactions as well. I like to think that there's those two ways of thinking about that. So we're going to have a wee look at the properties of carboxylic acids. In other words, why we're interested in it in the first place. And carboxylic acids, like the alcohols, are super useful. They can be used in preservatives, they can be used in soaps, which we'll focus on if you continue on to higher level. They can even be used in medicines. And an example of that is perhaps something that you use in everyday life. Vinegar is just a solution of a carboxylic acid. It's just ethanoic acid in a water solution. So that would be a chemical formula not just for vinegar, but for a carboxylic acid too, which we now know. And we would know how to name it because it has 2 carbons. It contains the COOH carboxyl functional group. So we know that that is ethanoic acid. And also, it is an acid. So can it be involved in neutralization reactions? Well, yes, of course it can, because it's an acid. So if we think back to Unit 1, we should remember that when we have an acid and we react it with a base, remember a base is just something that neutralizes an acid, and if it's soluble we call it an alkali, then we would form a salt and water. And the exact same is true for carboxylic acids. Yes, it's a named particular type of acid, but all acids and all bases will react together to form a salt and water. So that's something we need to look out for too. And in fact, there's a special way that we now need to name those salts, because before it would be just as simple as taking the type of acid that we have, for example, hydrochloric acid, and reacting it with a base, for example, sodium hydroxide. And then the salt to name would be easy enough. It would be sodium chloride. The chloride coming from the hydrochloric acid. But that's not the type of acid we have here. We have a carboxylic acid. And those have particular salt names. So if we have an ending that is anoic acid, in other words, a carboxylic acid, our ending for the salt now has to become something anoate. And to show you this by example, if we have methanoic acid reacting with, I'll just stick with the same example, sodium hydroxide, a common base, then our new name would be sodium, because it comes from the sodium part of the base, methanoate. And it's meth because it comes from methanoic acid, and it's methanoate with that anoate ending because it's a carboxylic acid. And you can go through each of the carboxylic acids with each of the prefixes, ethanoic, propanoic, butanoic, etc. And they would all have the same ending, ethanoate, propanoate, butanoate, etc., etc. And just always remember to include your water in the reaction as well. So that shows us that carboxylic acids are useful in lots and lots of different reactions, and a variety of different reactions within society that are very useful, often in our everyday lives. So not only do we know how to name them and how to draw them and how to identify them, but we know that they have various uses in our lives